So today we're talking about, this is a new test called the alternating series test. And this is where every other term is going to be subtracted. So if if a sub n is greater than 0, then the alternating series of -1 to the n. So that's -1 to the n is going to just keep on alternating between multiplying the rule of sequence with -1 or with a +1, because -1 to the first power will be negative, -1 to the second power will be a positive. So this is the alternator. It's just changing every other term to be a negative. So you can imagine when we have this alternating, if every other term is getting subtracted, then technically it should be easier for our series to converge. And so normally, if it was just limit as n approaches infinity of a sub n is equal to 0, we would say by the nth term test, this is not enough, right? This is not, it's a good condition for us to test further if there's a possibility that it may converge, but it's no guarantee that it will converge. But the fact that we're subtracting every other term, this would be enough. This will be enough for our series to converge. This second condition is saying that the absolute value of a sub n plus 1 is less than or equal to a sub n. Each term is smaller than the previous term. And it feels like as if we have the first condition met, then the second one should go hand in hand. But I think there is maybe an obscure situation where it fulfills the first condition, but not the second. So that's why we have to write out both these conditions, even though for most of our problems, if it passed the first condition, it's probably going to, we're going to be able to get alternating series test to be true, or our series to converge. So just a quick example here of if we just look at the harmonic series, right? This 1 over n, we know that this is a p series that does not converge. It's really close though, because the limit as n approaches infinity of a sub n does equal to 0, but we talked about how this will be an inconclusive n-term test. It's pretty much right at the edge. It almost converges, but not quite. It's just kind of inching up towards infinity. It's never going to quite have a ceiling that it touches. But if you look at the second scenario, where if I'm subtracting every other term, subtracting 1, -1, -1/3, -1/5, then you can imagine that this will have an easier time to converge because you're subtracting all these terms out of that series. And so if there's an alternator, this would be enough for the series to converge. Now, if it's an alternating series and this is not true, then the series will diverge by the nth term test, right? The alternator can only make so much impact, can only make an impact up to a certain point, but it needs this at least to go to 0. If it doesn't go to 0, then it doesn't matter how many terms we subtract. The sum is going to head up towards infinity. Ways to check if a sub n is decreasing. We can take the first derivative and see if it's negative. Usually it is obvious. We can also manipulate a sub n plus 1 and a sub n. Take the next term, divide it by the term before it. If it's less than or equal to 1, if the ratio is less than or equal to 1, then we know that each term is getting smaller. All right, so number 1, determine if the series converge or diverge. Number 1, we have an alternator. We're basically starting the first step like as if it were nth term test. It's just that the condition, it's going to be a little bit easier. Okay, so I have an alternator. I know that the limit as n approaches infinity of 1 over n does equal to 0. So normally we would say inconclusive nth term tests, but because of the alternator, it's good enough for us to say, yes, this series will converge. And also, let's just go ahead and also write out our second condition just to make sure we've covered all of our ground here. And we know this is true. We don't even have to test it. We can just write out that the fact that, technically we are covering all the bases in terms of our conditions. So we can say our series converges by alternating series test. And this is enough for us to as justification. We don't have to go through and show that the next term is smaller than the first one. On the AP exam, this will be sufficient. Number 2, we have an alternator. Your alternator can either be -1 to the n plus 1 or -1 to the n. Either one is fine. It's just that we're maybe subtracting the term after the first one instead of the first one, but it's still an alternating series. So either one can fit the criteria. So these are interchangeable in terms of alternator. All right, so all we need is to show that this limit of my rule of sequence approaches 0. And we know that if we're approaching infinity, if we're trying to find the limit as n approaches infinity, we just compare degrees. The degree in the denominator is larger than the numerator, so the limit does equal to 0. It's like as if we're finding horizontal asymptote. It does equal to 0. This is good enough. The alternator helps it to allow us to say this is good enough for our series to converge. All right, number 3. We have an alternator, -1 to the n plus 1. So all we need to show is, does the limit as n approaches infinity of my rule of sequence, does it go to 0? What do we see here? It's not, right? Equals 1. The limit as n approaches infinity of a sub n does not equal to 0, right? Now, if our limit doesn't equal to 0, we're not going to say that this diverges by alternating series test. We're going to say what? This diverges by what? Yes, diverges by nth term. So I just want to make that distinction. If your alternating series converges, you're going to say converge by AST. But if your alternating series diverges, you're going to say by the nth term test. All right, number 4, cosine of n pi. Let's talk about what happens if I were to plug 1, 2, 3, and 4 in. So I'm going to test it out to see what happens here. So cosine of pi, what's that equal to? -1. Okay, I'm going to increase n by 1. So cosine of 2 pi, what does that give me? Cosine of 3 pi -1. So basically, this is the what? This is as an alternator, using trig to disguise an alternator. So this cosine n pi is same thing as a -1 to the n or -1 to the n plus 1. So this acts as an alternator. So number 4 is essentially the same thing as number 1, right? So we're going to get the same conclusion. So I just want to show that sometimes trig can be used to hide or disguise an alternator or act as an alternator. All right, number 5, the following is not an alternating series. Look carefully to see if we can tell why or why not. I mean, we definitely see the -1 to the n, but this cosine of n pi may end up canceling out the alternating that series that this is doing here. So let's just test each of the n values out. So let's say we test n equals 1. If I plug 1 in for n, I get -1 to the first power, that's a negative number, times cosine of pi. And negative times negative gives me positive. And if I test n equals 2, I get -1 squared times cosine of 2 pi. Positive times positive is +1. So it looks like this is not doing the job of doing an alternator, right? You have two alternating series kind of clashing in a way where they're always giving me a +1. So really, this is just n over n plus 1 or n over n squared plus 1. Okay, the limit of this goes to what? 0. Is this good enough for us to say this converges? No, right? So if we go through n-term test and if we get this result, it's inconclusive. And if we get an inconclusive result, that means we got to do another test. We got to find another test for us to use. Maybe for this, it would be a good one for us to use either direct comparison or limit comparison, but I think we prefer limit comparison if we're given the choice. So let's see if limit comparison can help us make our conclusion. What's a comparison partner that we can get out of this? 1 over n, right? If I was to strip away that +1 and just get this n over n squared as reduced as possible, I get 1 over n. So I'm going to compare with 1 over n. Now we know that 1 over n diverges. So if the limit of one over the other can produce a real number, then we know this series also must diverge. So limit as n approaches infinity, n over n squared plus 1. I'm dividing this with this, and dividing by this, the same thing as multiplying by the reciprocal. So I get n squared over n squared plus 1. This gives me 1 over 1. I get a real number. So if I get a real number, then I know that I can say these two must share the same behavior. So we can say our series diverge by LCT. Okay, I just have a little bit of notes to go over on the next page, and then we can just spend the rest of the class just getting practice. Let me see. Okay, 37. I may do more practice with this tomorrow because some of these tests we may not have covered yet. That's okay. No, we can work around it. Some of these we haven't learned yet, but okay. So let me go through the notes here. This is absolute versus conditional convergence. So we have three possibilities regarding a series dealing with convergence or divergence. If we have a series that converges absolutely or absolute convergence, that means that a series does not need the help of an alternator to make it converging. So if there's an alternator, but if I can strip away the alternator and still show that the series converges, then we call that absolute convergence. An example would be -1 to the n of 1 over n squared. Okay. We know that there's an alternator here, but we don't need the alternator because 1 over n squared is going to converge on its own because it's p series, right? It's good enough for it to converge. So this is considered absolute convergence. Conditional convergence is where on its own it'll converge. It needs an alternator to cause that diverging series to become converging. So an example of that would be a harmonic series. Right? On its own, it diverges, but with the help of an alternator, it does meet the criteria of the limit approaching 0. So this could be considered a conditional convergence, where without it, it would diverge, but with it, it converges. Now, a completely diverging series would be one where it doesn't matter if there's an alternator or not, it's going to diverge either way. So let's say I had n squared, right? N squared, this series is getting larger and larger. It doesn't matter that I'm subtracting every other term out. This is going to diverge on its own, right? If it's going to fail the nth term test, it doesn't matter what the alternator does. It's going to diverge on its own. It's going to diverge regardless, regardless of the alternator. We'll come back to number 1. We haven't learned ratio test yet. But if you look at number 2 here, -1 to the n plus 1, we definitely have an alternator. Let's look at the rule of sequence without the alternator. It's just 1 over cube root of n. This is really the same thing as what? 1 over n to the 1/3. On its own, would it converge or diverge? Diverge because of what? P series. Yeah, P series or P value is less than 1. It's going to diverge on its own. However, with the alternator, maybe it'll converge because the limit as n approaches infinity of 1 over n to the 1/3 does equal to 0, right? So it doesn't converge because of P series, but it does meet this criteria for an alternating series. So we can say that this series converges conditionally. Right? On its own, it diverges, but with the help of an alternator, it does become convergent. Number 3, we have a alternating series again, but the limit as n approaches infinity of n over n plus 2 is equal to what? 1. What does that tell us? Diverges by what? N term. So this series diverges. It's not converging absolutely. It's not converging conditionally. It is just diverges by n term test. Okay, we'll skip 4 and 5 since those are. We'll come back to that after we learn ratio test. Okay, next page. All right, so let's go ahead and just try each of these problems. So go ahead and read it, try the problem. I'll put the key up, and we're just going to use the rest of the class just to get practice with these problems. Okay. Yeah, we'll just spend the next 15 minutes, see how far we can get. Everybody okay with 1 and 2? All right, everybody good with 38? I guess number six is an example where there's an alternating series, the limit as a of n is eventually approaching zero, but it's kind of jumping back and forth, but it doesn't quite meet that second condition where um, every term and the term before it is creating a ratio that's less than one. Okay, your homework, page 30 to 43. I'll send out a reminder this afternoon. Then tomorrow we'll finish up with ratio and root tests. And we can also talk about the quiz next Friday, which would just be over the tests before the comparison tests. Bye, computer boss. Okay, yeah. Yeah. Thanks.
Oh, I think you went full of the class.
Oh, no.
It's the group.
Oh.
They did, and then the other group looked like Adam and everybody. Like that was code one.
Yeah. Oh, that, yeah.
Yeah, they did okay.
It's a check.
We do better.
Yeah, yeah. Well, honestly, it was like pretty balanced. They're talking.
Oh.
I was like one row. I don't know. Like. I took a picture of the seal. Oh, sure. Not the awakening much. Don't you know the testament?
Yeah, those reasons, the treatment type of life.
I don't think Max is like either.
It's gonna be here.
Well, true. Well, yeah. No, like when.
Nothing happens to every, like, these. What is it? When you think there's, it's already, like, you can't make building. That's some areas like that. Right?
And did this good enough for like the nation?
Yeah.
Yeah.
When you go down.
Oh, yeah. That was pretty.
You start like words that you don't know underline.
Yeah.
I underline it with a lot. Right.